Hello there, so we're going to have a quick gander at functions. So basic function notation, we'll use bubbles to kind of help us here. So a function will map, and one of the words you can use is map or hit or move or input output or generate. Move stuff from what's called a domain into a range. Okay, so it's very specific. So for example, if I have a function, and this function, let's say, is x squared, and I have 1, 2, 3, 4, and these are in my domain, then my range will be 1 squared, 2 squared, 3 squared, and 4 squared. Okay, now most of your domains will be your natural numbers, integers, your rationals, could be anything in your domain. Now, what you can have as well is you can have a codomain. So the difference being that the domain and the range are your inputs and outputs, but your codomain could be all the possible outputs that are not generated. So for example, these are all natural numbers. So my domain is the natural numbers, my range is the natural numbers, but it's not all the natural numbers, but my codomain would be the set of all possible natural numbers, of which the range is a subset. So there's some very kind of easy things to kind of figure out. Okay? So how do you know if something is a function? It's very, very simple. Okay, let's take two examples. Let's take x squared plus y squared is equal to 1. So in other words, a circle with a center of 0, 0 and a radius of 1. Okay, and that's x squared plus y squared is equal to 1. Okay, and let's take another function. Okay, let's take, I don't know, let's take x cubed plus 3x squared plus 4x plus 5. Okay, so there's two equations. One of them is a function, one of them is not. How do you know the difference? The difference is very simple. Okay, if you draw a vertical line through the x-axis, if it intersects with the line of the graph more than once, it's not a function. So as you can see here on this one, as I draw vertical lines, it only crosses or intersects with the curve once, whereas here multiple times. So this is a function and this is not a function. So that's your simplest test. Sketch the graph, don't have to draw it, sketch it, drop vertical lines, and if those vertical lines intersect more than once, it's not. Okay, so it's a very simple test to see whether or not it is. Okay, so now composite functions. So some people call these nested functions. They can be written in different ways. So let's say f of x is equal to 2x plus 4 and g of x is equal to x squared plus 2. So there's different ways this can be shown. So for example, I've seen it where it's been f of g is equal to 2. I've also seen it f of the g of x, okay? And then I've also seen it as f0g, okay? So all they mean is the same thing. And basically what they're saying is get the g of x, substitute it in for where you'd see x in the f of x, and then do something to it. Okay, so this case it's saying, in this case what they'd be saying is take the g of x, pop it in here. So the f of x is 2x plus 4. So if I replace that with g, that means that's 2 instead of x, and then make the answer equal to 2. So that would be 2x squared plus 4 plus 4 equals 2. That'll be 2x squared plus 8, take away 2 plus 6. So that would be your new function. And they'd be the same thing, except you wouldn't be making it equal to 2, you'd just be nesting the functions. In other words, in this case, subbing the g of x into the f of x, you'd just get down to this point here. So in both these cases, you wouldn't be making it equal to 2, you'd just be 2x squared plus 8. Okay? So you might get something like that. Now, the types of functions. This is probably what you're here to see. Okay? So, for the leave insert, we have 3 types of functions. We have injective, we have surjective, and we have bijective. Okay? So I'm going to explain them diagrammatically and then maybe explain them in kind of a simpler terms. Let's take the injective one. Okay? So, in the injective function, you've got your domain, so let's say 1, 2, 3, 4, and then you got your codomain. Okay? Let's say, 5, 6, 7, 8, and 9. Now, in an injective function, everything from the domain is used. It doesn't really make a difference what the function is. All you need to know is that everything from the domain is used, okay, once and individually. And that doesn't mean that everything in the codomain gets something. So poor number 9 didn't have a corresponding original input. But that's fine. So long as everything that is individually mapped onto. Okay? So that's what an injective means. So to kind of put it into a very simple, imagine you had a classroom. Okay? And this particular classroom, let's say you have 30 kids. Okay, but let's say you have sweets left over from Christmas and you have 25 different sweets. Okay, and you're going to give the sweets to the kids. Okay, so you're going to give each kid an individual sweet, and each individual sweet is going to be different. That's an injective operation, because even though every kid doesn't get a sweet, you have given 25 individual sweets and your box is empty. So this is empty, you have given individuals. It doesn't make a difference if there's kids left over, as long as every kid who did get one got an individual. That's injective. Okay, so let's have a look at surjective. Okay, so in surjective, it works kind of like the other way around. Okay, so it really doesn't matter what's in the domain. What matters is that everything in the codomain gets something. So for example, now you're thinking to yourself, how will some operation will allow 2 things from the domain to map onto the same output in the codomain or range. Okay? So that's the idea of it. Now, let's use it in our scenario here. Okay? So what it means is that I have 30 sweets and I have 30 kids. Okay, so every kid gets a sweet. However, they're not all guaranteed to get an individual sweet. Some of the kids might get the same sweet as some of the other kids, but every kid got a sweet. So it's really the codomain or the range that matters. Everything in the codomain or range will be mapped. In other words, they will be generated by something, but there's no guarantee they'll be individually, like they are in the injective, that they're individualized. Their production or how they're output it. It just matters that everything there came from something. Not from everything there. Everything there came from something there. Okay? So, number 3. Well, this is an obvious one. It's the combination of the other two. In a bijective, not only does every number generate a corresponding number, 6, 7, 8, 9, 10, but it's individualized and unique. So you can see it takes the individualization of this with the everyone getting something from this. So when you combine the injective and surjective, you get your bijective. So what this means in terms of our kids is, like the surjective, 30 sweets give 30 kids. But like the injective, they're all individual. Okay, so I hope that makes sense to you in terms of the injective, surjective, and bijective. Now, how to test? Well, it's very simple to test if something is injective. Okay, so I'll show you algebraically how I would show that. So let's say I have a function, and I want to show that this is injective. Now, visually, how I could show this is injective is I could draw it if it's a straight line. I know one in, one out, and you're always that's going to work. But that's algebraically. Let's say I have two numbers that I want to put into this function. Let's say I want to get the f of a, and I want to get the f of b. Okay, and a is not equal to b. So I'm going to set this up as a kind of a contradiction. So I'm saying that a and b are uniquely different. Okay, so let's pop them in. I'm going to put 3 times a plus 5, and then let's put in b, 3 times b plus 5. But now let's say that their outcomes are the same. So remember, if they're injective, it's unique. If it's surjective, then that is possible that two different numbers can go in and the same number can come out. So let's see, is this true? So I'm saying that two numbers can go in and one number can come out. That's what I'm saying there. But I'm trying to prove it injective, which is not the case with this. So I'm going to see, can I trip myself up? So let's subtract 5 on both sides. And let's divide both sides by 3. So there's my contradiction. I said they weren't the same, but if it's an injective function, those two numbers would have to be the same, because there's no way of having two different numbers generating the same output in an injective function. They'd have to be the same number in order to generate the same output. Okay, so there's a nice little trick for doing that. Okay, now the last kind of area of this is to find the inverse of a function. Okay, so I'm going to show you how to find the inverse of a function. So let's declare a function. So let's say we have f of x equal to x cubed plus 1, and I want to find its inverse. Well, the first thing I'm going to do is just replace the f of x with another common letter, y. Okay, so the idea is to rearrange this so you get it in terms of x. Get it in terms, or isolate x on its own. So let's isolate x on its own. We'll have x cubed is equal to y minus 1, and because I'm cubing it, I can get the cubed root to the other side. X would be equal to y minus 1 to the power of a third, or x would be equal to the cubed root of y minus 1. Now, when you've got it to that far, how do you show that it's an inverted function? Well, you can't use x and y the way we just don't use it there. We have to rearrange it. So this will become, x to the minus 1. So you just put a little minus 1 to say that it's an inverted function, and then just replace the y with x. So similarly here, just f of x to the minus 1 equal to x minus 1 cubed. So, how do we test this? Okay. Well, there's a couple of ways you can test it. Okay. What you can do is, let's go back to our original function. Let's put in a number. Okay. Let's get the f of 2. So if I pop that into the original function, that's going to give me 2 cubed plus 1, which is 2 cubed is 8 plus 1 is 9. So the f of 2 is 9. So now let's reverse the process. Let's put 9 into our inverted function. Okay? And we should get out 2. So in our inverted function, let's put in 9. So that's the cubed root of 9 minus 1. So that's equal to the cubed root of 8, which is 2. So that is an inverted function because when I put 2 into the original, I got 9 out. And when I put 9 into the inverted function, I get 2 out. So that's how you know to prove it. Okay?